reference to his work, and it's great to be able to hear him tell us about it himself.
Thank you very much. Well, first, I'd like to thank organizers for inviting me to this very interesting and wonderful workshop. And here today, I'd like to talk about our recent works on excited state, especially in conformal field theory and its calculation of entanglement entropy. And we'd like to explain some rather universal behavior and property of this entanglement entropy by using ADS-CFT for this excited states in conformal field theory. And this talk is based on this series of papers and based on the collaboration with Jyotimoi Bhattacharya, who is a postdoc at the Kaburi IPMU, and Masahiro Nozaki and Tokiro Nonosawa, and they are graduate student in YITP, Yukawa Institute, in Kyoto University, and Andrea Prudentiati, he is currently postdoc at the YITP. And finally, Tomonori Ugati, who is my student, but he belongs to Kaburi IPMU. Okay, so let me begin with introduction. So maybe you already heard maybe many things about entanglement, but here just summarize the basic concept. As the entanglement entropy, quantum entanglement is quite an important concept which connects this quantum manifold system and quantum information theory. And entanglement entropy is the explicit measure of this quantum entanglement. And more practically, it actually measures the amount of active degree of freedom or the amount of information. And the reason why we are interested in this is really broad in many senses. But for example, especially in the context of condensed matter systems, recently this entanglement entropy has been heavily used as some numerical observable quantities. So this is quite still difficult to observe entanglement entropy in real experiments. This is a quite interesting developed subject, but we are far from the answer. But this entanglement entropy can be a useful quantity which can be computed in numerical calculations in relatively easy way. So people use this numerical experiment to detect some basic property of condensed matter systems. So we can start with very complicated Hamiltonian, which is not exactly solvable, but still we can do some numerical calculations. But then we should ask what quantity we should look at. And if we want to look at some universal quantity like central charge or some a generalization of central charge in odd dimension, something people call the topological entropy or some F function, then we can look at the best way to look at it to do numerical calculation of this entanglement entropy. So in this way, we can somehow use this quantity. And this advantage of this entanglement entropy is the several advantages. But so first of all, it is a quantum order parameter. So in a quantum mechanics, there are very complicated structure of ground state, which is quantum entanglement. So we can classify quantum phases by looking at this entanglement entropy. It's a sort of some generalization of Wilson rooms in gauge theory. And also for string theorists, so this entanglement entropy is quite useful bridge which connects gravity theory and condensed matter physics. And so gravity we have metric, and in condensed matter system we have ground state wave function, but they it looks like slightly different. But if we use entanglement, so if we know this ground state wave function, it is obvious to compute entanglement entropy, even though it's sometimes quite difficult, but in principle we can define entanglement entropy from wave function. On the other hand, if we have gravities, as we quickly review, the ADS-CFT tells us that gravitation, this metric in gravities can be computed as it's mapped to some area of minimal surface, and which actually computes this entanglement. So in this way, this condensed matter system, or more generally, quantum many body system is closely related to gravity by using this idea. And finally, so if we are interested in application to non-equilibrium physics, which is quite difficult to understand even now, but maybe this entanglement entropy is a good quantity because we can define this quantity in any quantum manifold system. So just standard entropy, thermodynamic entropy, can be only defined in thermodynamic equilibrium or some static stationary system, but this quantity is quite robust, and you can define any quantum manifold systems far from equilibrium. So the issue which we would like to discuss in this talk is, very roughly speaking, the connection between the amount of information and the amount of energy of some given quantum manifold system. So idea is quite naive. So we just interested in first law of thermodynamics. So we know this first law of thermodynamics very well. So it is some change of entropy is related to change of energy. This TdS equal to dE, and this coefficient is just temperature of the system. So this, the question which I'd like to ask is very simple-minded. So can we find some analogous relation in any quantum many-variable systems which are rather far from equilibrium, just without using any equilibrium? So naively we expect something like this kind of relation by using entanglement entropy, as already mentioned. So we can just we cannot use standard entropy, but we can always use this entanglement entropy. But to define entanglement entropy, we have to specify subsystem, and the other part, I'll quickly review, but the other part is trace out. So this entanglement entropy for subsystem A, and that's the difference. It should be proportional to energy, because anyway, this entropy and carries information amount. This carries this is a measure of amount of information should be related to energy, and its coefficient we can call some entanglement temperature. We don't know the interpretation of this yet, but somehow we can define this kind of coefficient. So maybe we may have this kind of relation. That's what we'd like to discuss in this talk.
Far from equilibrium, I guess is. I think I know.
Yeah.
It's actually more like highly excited state.
Yeah.
Right? It's not like
Exactly. You're right. But in this talk, probably I will focus on weakly excited systems because of some calculational reason. But it's also this kind of thing is involved.
Like you think the system
Yeah.
in a highly excited state, and then that kind of talk is more like you just look at
that's
highly
correct.
excited state.
I totally agree. And this is quite interesting. But this kind of relation, in the end, what I'd like to say is that this kind of relation only we can only prove for this weakly excited state. So for highly excited state, we are still not clear. This kind of thing. We can get some result, but its result is not universal. That's very good point. Okay. So the content of my talk is follows. So we first give some basic facts about entanglement. Maybe you already heard. But then we got some analog of first law, which I just explained for entanglement entropy. We derive this property by ADS-CFT, and we introduce some new quantity called entanglement density, which is sometimes useful for excitation which are not homogeneous. If we have some local excitation, which we excite on local regions, sometimes entanglement entropy is good, but not so clear. It does not give a clear idea. But this entanglement density is somehow useful quantity to characterize a state in such case. And then by using this, we study this local quenches. Quench means excitation, sudden excitation, and we locally excite some region, and we give some holographic description of that. And in the end, we like to ask a more ambitious question that what is the counterpart of Einstein equation in terms of entanglement entropy? We give some result of particular case, so we'd like to discuss the result in the end. So basically, concept of entanglement entropy, the definition is very simple, and we divide total system into two parts, HA times HB, this direct product. In a spin chain, we can just artificially cut it at some point. We just call this A and B. And then we define reduced density matrix low way, which is defined by trace out the other part B. So this density matrix for A. So we want to erase this part, so we just trace out this region B. And low tot is the original just original density matrix, total density matrix. And by using this somehow coarse-grained density matrix, reduced density matrix, we can define this entanglement entropy just to be a standard Von-Neumann entropy minus trace law log rho. In quantum field theory, we just need to specify the boundary between A and B. So if we specify this, then we specify this division, this factorization of Hilbert space. And for each choice, we have one entropy. So that case, there are infinitely many different choices, and that means we have infinitely many different entropy. So basic property of this entanglement entropy is these two, and there are something more, but we don't use in this talk, so just write it. So the simplest one is that we assume total system is a pure state, then SA equal to SB. A is a complement, the other part of A. So that means the entanglement entropy is not extensive. It's not thermodynamical, and especially this pure state. But if we go to some mixed state and really approaching this canonical, high temperature canonical ensemble, a very highly mixed state, then this is no longer true, and there are some part which looks like extensive. but at the 0 temperature pure state, it is always 2. And the second one is non-trivial one is called strong subadditivity, and I'm using this property slightly later. So it's proven by first this guy. And this inequality is like summarized this way. The second one is not independent, so we can just focus on first one. And we divide total space into A, B, C, so that there are no overlap between A and B and B and C. We don't care the topology. We just divide this way. And we can assume total density matrix, any density matrix, which is even mixed state, any density matrix fine. Then this A plus B means, I should say this is A union B, this is combined region for entropy for this region, and this region is always greater than this continuation. So this is some inequality, and this is somehow sort of some, people call it some concavity of entropy. And indeed, if we assume this ABC is originally just real some set, some Hilbert space, but naively we just replace ABC as numbers, then we have this inequality. And especially we can pick up, we assume that these two guys are same. Then we have this x, this x plus y over 2 is A plus B and also B plus C. Then we get this inequality from this equation. And this clearly shows that the second derivative is negative or is really concave function in this sense. So this is an intuitive understanding of this strong subadditivity. So on the other hand, we can do the calculation in ADS-CFT by using ADS-CFT. This is a holographic calculation. And so the result is calculation is very simple, that we have some untitled space, and we have conformal theory. This is a standard setup of ADS-CFT. It's a bulk to boundary correspondence. And in the boundary, we have A and B to define entanglement entropy. So this, we are focusing on this boundary of A, which is the most important part of which defines this entropy as A. And this entanglement entropy as A in this conformal theory is defined to be just extending this boundary towards the bulk. This is a codimension 2 surface in total space-time. And we pick, there are such many, infinitely many different extensions, but we pick up minimal area, which is minimized area functional. So this is what we call gamma A. And then, so of course this gamma A should end on this boundary of A and should be topologically equivalent homologous to each other. And we get, so this surface, definite surface, and we compute this area and divide it by 4D Newton, exactly the same as black hole entropy, so we get this entanglement entropy. So this is a holographic calculation, and in time-dependent background, this minimization property is somehow not good, because in time dependence we have to deal with Lorentzian geometry, because there are no simple time slice. So here we are actually naturally take some Euclidean geometry or take some natural time slice in static geometry, but in generic we don't have some static. No longer static, and then there are no nice time slice. So we have to deal with Lorentzian geometry. So then there are no minimal area, really minimized area. So we have to, in that case, we have to use extremal surface, and we take some area functional and extremalize, and this is a covariant entanglement entropy, which I proposed with Fubeni and Rangamani. So using this, we use this, and so this kind of holographic calculation has been confirmed in many ways. And this area law is a basic property and strong subadditivity and conformal anomaly. And but recently there are nice developments in this direction. There are some proof by Lukowitz and Margasena, who proves this holographic calculation, especially for Euclidean ADS-CFT setup. But still, time-dependent background. Covariant precision has not been proven yet, but there are interesting developments. For example, the confirmation, strong subadditivity, and so on.
Tadashi, can I ask you? You mentioned the Lefkowitz-Maldacena proof, and of course, they have certain assumptions in their proof. One being that there's replica symmetry, and I think implicitly also that with given Euclidean boundary conditions, with the given boundary conditions, the Euclidean bulk of interest is the dominant saddle point for the partition function, whereas we're interested in cases where it's subdominant saddle as well. So is there anything known about either of those cases or extensions?
Replica symmetry, anyway, we are doing this replica calculation in CFT side also. that also assumes some analytical continuation about this replica number n. And similar thing we assume in gravity side.
That's all fine. My question is, surely there exist cases, if we work hard enough, that break replica symmetry. And
yeah. I think they also commented that possibility.
Yeah,
in some cases that's possible.
Do we know whether this proposal is the correct one, or we have any evidence for whether it's correct or not for cases that break replica symmetry?
I think it's replica symmetry is broken, then probably result is modified, not the area rho. I think that's intuitively.
Probably which result is modified?
This area, minimal area.
It's no longer area.
Should be modified. But of course, I didn't do.
Are there any examples that have been studied?
I think people are interested in that, but I think still we don't have definitive.
And on the other hand, I mean, we do have evidence that when there's a subdominant saddle point, like a small Schwarzschild ADS black hole, that this still seems to work. So it seems like there's room for additional proof even beyond Lefkowitz and Maldacena have done. In fact, there's a large category. It seems like they have not proven that it works for things involving small black holes, whereas all the standard checks and so forth still work. So it seems like there's
Okay, that's it. Yeah, that's quite an interesting point. But sorry, I don't have a definite idea about now. But it's quite interesting.
What is the meaning in the field theory when you break replica symmetry? I only know it right from spin glasses and so forth. Well, what happens, generic field theory like this?
But that's right. This spin glass, this replica is different from this replica.
Yeah, sure. Question: what the heck is the meaning of that replica symmetry break in the field theory? I guess it's unknown.
For most field theory, you don't expect it to happen. Yeah. The intuition that was gained, in fact, from spin glasses is you need systems that have an enormous number of states which are almost degenerate for it to happen. And therefore, I think it's an exception, really, and it doesn't apply to many systems. In fact, we tried to find symmetry break in ADS CFT after the work of Takayanagi and Briu, and we didn't find anywhere. Of course, we couldn't prove that it cannot happen, but it seems that these types of systems are not the types that have it.
So possibly large N removes.
Large N is not enough. In fact, there is a large N system that has in fact spin glass behavior, but it's important that the degrees of freedom are discrete, not continuous.
So I know deeply about the consistency, right? But you don't like all that.
So I think it's quite interesting to have some field theory example where replica symmetry is broken. But so far there are nothing, so there are no strong motivation to study it. That's I think, but it's quite an interesting problem to look at. So also there are also developments about correction to this holographic formula in beyond this supergravity limit. But maybe probably there are talk here, so I'm not going to mention in detail. Okay, so now I'd like to come back to the original problem, which is some analog of first law of this excited state. So entanglement entropy has a UV divergence, which is characterized by so-called area law. And so we'd like to somehow remove this divergence to get a nice quantity. So we mainly work on this quantity called delta S, which is just entanglement entropy for some excited states, which are looking at minus some ground state entanglement entropy, just subtract. Area law divergence is just subtract. And then this is always finite, and we'd like to compare this delta SA with this energy, which is included in some subsystem A, not total system, just subsystem A, just the integral of this energy storage tensor over this region A. So very, very simple setup. So the holographic, we go to the holographic calculation, but the holographic calculation tells us very simple result. So we are looking at some asymptotically ADS background, which is dual to some excited state in CFT. So if we have purely ADS background, of course it is dual to ground state of conformal field theory, but we are talking about excited state. So then infrared region, when Z is a radial coordinate of this metric, it's slightly modified. But we don't care the detail of infrared modification. We just talk about UV behavior. So the reason why we look at UV is we get because we want to get some universal result. And the UV region actually corresponds to the small subsystem of this entanglement entropy. So we will focus on small subsystem later. So we just look at UV. Then this is this Fz and Zz. When they are 1, this is just pure areas, as we know very well. And it's, for example, if we imagine black hole, it's have some this kind of modification. But this kind of modification is universal, assuming asymptotic area space-time. And we don't care whether we have black hole horizon or some star or some other object. But always this kind of, this m and this minus m is dictated by this vacuum Einstein equation, where there are no source here, but there are source here in the infrared. So then anyway, so this m is the area mass of this background, and this m is entered into this holographic energy stress tensor. So its energy density should be proportional to m. And this m characterizes the leading deformation of this background. And then we, in this background, we'd like to compute this entanglement entropy by assuming very small subsystem, so that L is the size of subsystem, and this m times L d plus 1 is much smaller than 1. This is assumption. Then we can always show that this this kind of proportional relation, delta S is proportional to delta E, and so this coefficient turns out to be always take this form. This which we naively call entanglement entropy, but its interpretation in terms of temperature is not clear here. But I just call it this way, and this C over L. C is some constant. This depends on the shape, but it only depends on the shape. And in this calculation, there are no other parameter appears here. So, for example, n or coupling constant doesn't appear here in area CFT calculation. So C especially takes a very simple value when, if we take this A to be round sphere, we can compute this analytically. But for generic shape, this is calculation of C is a bit technically complicated. Maybe there are some nice formula, but we don't know. But always, because of the dimension, it takes some C over L. L is the length of this subsystem. So anyway, in this way, we can confirm this kind of result, this holographic prediction. So consider some excited state in a CFT, but here we assume the translation, almost translation invariant and rotational invariant, because here this kind of assumption is already implicit. M is constant, doesn't depend on the position in transfer direction. And then we assume this size of subsystem is very small, or energy density is small, so that it satisfies this relation. Then this kind of first law-like relation is always satisfied. So delta SA is always proportional to delta EA, and its coefficient is always behave this kind of rather universal shape. So C is only depend on geometry.
So what else would it possibly depend on?
Sorry.
What else would it possibly depend on? This coefficient C?
Here. For example, Prof coupling and other dependent doesn't appear here.
But you're doing it at large coupling.
Yeah, right. But still, sometimes lambda appears, right? Some power of lambda. But somehow here it's no such.
But you say you can see from the CFT there's no dependence on coupling constants.
Yeah, the coupling was Prof coupling, right? In CFT there is a.
Sorry, this is a CFT argument?
Or no, this is a holographic argument.
This is just a prediction. Okay.
Yeah, prediction. Yeah. I'll come back. I'll mention.
And I'm sorry, I missed the details. This is for small perturbations around the ground
state.
Yeah,
right, exactly.
And in fact, you see there, this is the 1 plus 1 CFT only, or this is general?
No, so C is not central charge. This is just some constant. Maybe confused. Sorry, okay. Confused. Just some constant. Maybe you can alpha or some just constant, which is geometrical quantity.
Very simple question. Right? So when you restore explicit dimensions, it would be like h bar C of L bar C is the velocity of light. Right? So the entropy has to have dimensions of energy. Like you have length there, so you have an implicit h bar.
So the entropy is dimensionless?
Yeah, so the entropy has a dimension of energy, right? So you need h bar.
Yeah. H bar is that's what I said everything.
And the other question is, I guess you need here that somehow you have conformal invariance.
Conformal, yeah. Conformal invariance is very important. Exactly. That's right. Because we assume some this perturbation from AGS. But so the conformal invariance, but slightly we can generalize situations, so-called some more generic critical points where we have dynamical exponent, non-relativist. But still we can get a similar result. But now this L to power minus Z, because this is the energy dimension, to adjust it to have Z.
So that when there's a scale in the system, it will break down somehow.
Yeah, right. Exactly. That's right. We are talking about conformal.
So if you start with non-conformal ground state, and then slightly change the parameters?
Yeah, I think we still get this kind of proportional relation, but this T entanglement entropy is a more complicated expression, right? And mass, and also other kind of, yeah. Okay. Sorry.
When you take the first law-like relation, at some level, again, this is the definition of T entropy, just this derivative. And the prediction is just that T entropy is geometric, it doesn't depend on coupling constants, it's strong coupling.
Yeah, but actually, there are some cases where we can show this is exactly, even for any coupling constant. That's probably what I mentioned. So that is a case when the subsystem A is actually sphere, really round sphere, round ball. That case, actually, this Myers and collaborators, and also Jayas and collaborators shows that this kind of delta SA equal to this delta HA. Delta HA is something people call modular Hamiltonian or some entanglement Hamiltonian, which is just defined by log of rho A, density-reduced tensor matrix. And this is a sort of Lindblad Hamiltonian.
It's not the same energy you were measuring.
Exactly. But there is some nice formula, also this work out Cassini and Clayton Myers, which relates this delta HA to this TTT, previous this energy stress tensor. And by using that, actually, we can prove this relation. With this particular constant, this round sphere case we get. That is actually can be proven just using conformal invariance, without using any large Tofuft coupling and so on. But beyond that, if we are really interested in a more generic configuration of subsystem, then there are no nice results. But then because this kind of relation doesn't hold, and we don't know how to deal with in conformal field theory. For example, this delta SA is now linear combination of not only TTT but other components of energy stress tensor. If, for example, rotational invariance is broken, it's more very complicated. And yes.
I have the relation at the bottom is generic. It's just that delta HA is no longer local if you have a...
That's right, yeah. But then relation to TTT is not...
Right, so there's a complicated...
Okay, that's right, yeah. Thank you. Yeah, exactly. So, okay, yeah. This is, the meaning of this is quite complicated. Also, I should mention this kind of relation only true when we assume first order perturbation. If the perturbation is very large, this becomes actually inequality. It's not this kind of relation. So, if we are interested in generic excitation, it seems there are no universal features so far.
I usually find it. You start out from a ground state, and then you go to the excited state, and there you compute the entanglement spectrum.
Yeah. So exactly, entanglement spectrum. Yes. Okay, so for generic shape, actually, we don't know much about, but for spherical case, there are many progresses in this direction. Okay, so this is a story of this some analog first law, but I'd like to study more detailed structure. Yes.
How you said you can derive your previous slide from this result, but as you said, this result, the Myers et al. Result involves the Rindler-like Hamiltonian.
Yeah.
How do you turn it into the non-Rindler Hamiltonian? How do you get
non-Rindler Hamiltonian?
Again, that delta EA, if I understand, is just the integral of.
Yeah. So but also there's an express relation between this Rindler Hamiltonian, also this standard energy stress tensor. Just Rindler Hamiltonian and also energy stress, standard energy stress.
But it's not. The Rindler expression involves integrating TTT against some non-trivial function of x.
Right. Exactly. But it's a very simple function, only depend on radius.
Right. So how does it reduce to just integrating TTT against a flat measure?
Sorry. It's like some integral of this TTT, right? It's like so we have some this kind of region, and we define this radial direction, and it's like some function, and this TTT is now it's related to this something entanglement Hamiltonian. But this can be integral; it can be easily done, and so we can
under the assumption that TTT is constant, you can do the interval. Is that the
idea? Yeah. Right.
I see.
Yeah.
All right, and it turns out that the size of the sphere cancels out. It's only
yeah.
I see. All right.
Okay, so maybe I could see. So this, maybe let me introduce this quantity which I call entanglement density. So this is, so here I'd like to talk about the situation where there are no translational invariants. So we just want to measure the local correlation, local entanglement between some point and some other point. With here point is coordinate is L1 and the other point L2. If we naively think that entanglement entropy consists of this two-body entanglement, actually this is not true. We have many-body entanglement, but just we can sum over each this kind of two-body entanglement, right? So if we subsystem A, we pick up one point and the other point, and we integrate over all positions. That's this simple formula. And if we assume that we can take derivative of each point, L1, L2, each point, then we can extract some density of this two-body entanglement. But still, we can define some quantity by this equation. So this is something we call entanglement density. This roughly effectively measures this two-body entanglement. And the reason why we think this is a nice quantity is that this quantity can be shown to be non-negative. It's positive or zero because of this strong subjectivity. We have strong subjectivity, but somehow we can show this is always positive. So that means we can interpret this as some density, physical density. Yeah.
So it has two arguments, which are sort of the endpoint of that
two arguments,
region, yes. And then the sort of interpretation of that is that it's sort of entanglement between that.
Yeah,
sort of
just 2 points. 2 points. It's sort of 2-point function.
Okay.
Some analog of that, but
And this is for 1D system, spatial 1D system.
yeah, spatial. That's right. Yeah, exactly. Yeah. So we can somehow we have some generalization of that, but it's more complicated, so I don't define it. But it's the simplest case. It's this 1 plus 1D case.
And it diverges. X goes to Y.
And this is always finite.
It's always fine, even at the coincidence.
Coincident. Okay. Coincident it's divergent. Sorry, it's divergent. Coincident it's divergent. Sorry. Yeah. Because if you have log L, then we can take second derivative, certainly 1 over L square or something, which is delta. So the connect, so we can apply this previous first law in this for this entanglement density. So, but anyway, so this entanglement entropy delta SA is related to energy stress tensor or energy, because this is just come from first, which I call some analog first law previously, and we take L size L to be very small. And then in terms of this entanglement density, so we can take this, which I call this delta n. Delta n is a difference of this entanglement density compared, so some excited state minus some ground state value. So this difference, it's actually, and we think L goes to 0 by using this, we can just cut it. This is a twice derivative, so we can just cut it out. And we get the result is proportional to energy density with minus sign. So that means that for particular limit, this entanglement density is conserved quantity like this energy density. And in that sense, this entanglement density, originally it is, I mean based on this entanglement, but actually it's some generalization of this energy density, which is more basic quantity. It's a non-local version of this entanglement. Sorry, non-local version of energy density. So this actually we can also go more, and we can show this full conservation law of this entanglement density. So we have two arguments L1 each point, and we integrate over this region, and so that we integrate with respect to these two arguments, this L1, L2. Then we can show that this total integral is always conserved. There are no time evolution. So this I don't get into detail, but we can basically this comes from the fact that this looks like total derivative, and we just integrate twice. Naively we get 0, but this there are some surface terms we have to be careful. But this is actually turned out to be 0 because of this first law and also SA equal to SB. This is a pure state. We assume pure state and region.
You say there's full conservation, but you're using your first law, so this applies only to homogeneous states that are slightly excited above the vacuum. Is that right?
But this is quite general, and we don't need any homogeneous excitation or something, any excitation. So we can talk about any large amount excitation in this case.
The first law you're using there is which first law?
Okay. But first law, I said the first law, but we take L goes to 0 limit. Right? So this we get L goes to 0 limit. Then always this is true.
I see.
Because it's somewhat correlated. Energy density also correlated with this L. So this energy density is small. That means small perturbation, but actually that is the same as L goes to 0 limit. In this, yeah, that's actually good. So this is quite general.
You said pure state, right?
Pure state, yeah, that's the assumption. Yes, exactly. That's very big assumption. So somehow we get, but we don't know completely understand this conservation. So anyway, this looks some interesting quantities. I just want to use this quantity to study this local range. So the idea is of this local range, just local excitation. We have some conformal field theory on some space, and we take some region where we locally excited. This some region is excited, and maybe we can choose the subsystem A so that it's almost coincide with this local region, excited region. Then probably this entanglement entropy measures some amount of somehow information of this excitation. That's a basic idea which we'd like to use amount of quantum information excitation to here. So in that sense, there's some explicit example compared with previous universal analysis. So this so this is something called local quantum quench. But before that, maybe we should mention explain a little bit global quench, the standard quantum quench. So local means just really inhomogeneous, some localized on some particular region. But global means everywhere. We excite everything in a translational invariant way. So this summarization, this is called summarization because we excite the system. So under sudden change of Hamiltonian is called quantum quench and has been intensively studied in condensed matter physics and some theoretical aspects, and even realizing some experiment. This is mainly we follow this work by Calabrese and Cardi and their formulation. So, but nowadays there are lots of papers which discusses this kind of time dependence, and it's basically corresponds to black hole formation in Untitled Chapter space, and this is due to summarization in CFT, which we know probably now know very well. So this is a holographic description of global quench, and this calculation of entanglement entropy, especially Cardi and collaborators, shows that this is linearly after time evolution. Here, t equals 0, we excite the system. We do this quantum quench. We change suddenly some mass or some coupling constant. Then we excite the theory, but even though everything is pure state, so this entanglement entropy linearly increases, and after some time it saturates. So the time when we have the saturation is L over 2. L is the total size of this subsystem A. Length of subsystem A, and we start to somehow here, for example, then we take some time evolution at the speed of light. This is conformal field theory. Everything goes at the speed of light. Then 2t is this kind of entangled region separated by 2t after time evolution. So this when these two guys coincide, we have saturation. This is a simple example.
Sorry, but this result is universal. What are the conditions to get this linear and then saturation? For what model? Or for, yes, a conformal field theory?
Yeah, conformal
any conformal field theory.
Yeah. In 2D conformal field theory. Yeah, it's quite a generic argument. Which shows, but the detail, for example, here, initial point is not so clear. Also, detail here is not so clear. So this approximately we get this linear behavior. So, but we can also look at this entanglement density. So this is actually some advantage of this one. So yeah, of course, this kind of behavior we already explained, but more clearly we can compute this entanglement density. Then we have delta function at when L equals 2t. This means that exactly these 2 points are strongly entangled. This is separated by 2t. This point has a really delta functional peak of this entanglement density. And there are also some this region detail of this region is also reflected in this region. But in the end, when L equals 0, we have negative value, which is minus TTT. And previous this conservation law. Right? This conservation law means if we integrate of all of the region, this negative and positive, they completely cancel with each other. Some rule.
Just trying to read the picture well. What you're basically saying is, right, so you vary the distance between the 2 points, and then at the moment that these sort of entanglement fronts snap by, you get the delta function.
Yeah.
That's right. I like that.
Yeah.
The fronts that it's our philosophy.
Yeah. So how should we interpret this negative bit? Is this some negative information?
But this is some delta n. So the total n is always positive. But somehow this means that excitation in conformal field theory is first to remove some entanglement in UB and put it in the infrared. That's what this somehow tells us.
So actually, this delta function comes because of the kink at the...
Yeah, exactly. So because this gradient changes, we take a second derivative. So this first gives theta function, and we take one more derivative, it becomes delta function.
But my understanding was in holographic models that step is smoothed out, right? There's some polynomial of.
Okay, yeah. So that means, So detail of this structure also reflects the detailed shape of this one. Yeah, you are right. Yeah, maybe it's a Gaussian or something like that. Yeah, also same thing. Yeah. Okay. So, but now go back to local case. So usually, so people mainly work. So in condensed model side, people often consider this kind of model. So where we have two separated chain and we join at some point, and then that means we suddenly introduce some local Hamiltonian here. So we excite some system locally. But here we just talk about more generic case. Just we excite some point. We start with connected chain or connected line and just suddenly excite this. And we just give some very simple holographic description of that. So we define this alpha to be the size of excitation here. And so our claim is that very simple model. So we have Untitled Chapter space and just consider some falling particle. So we have some massive particle m, whose mass is m, in Poincare radius. And if we put some particle, because of the mass, then there is a gravitational force, which this particles go to the infrared region, pushed to be. So this trajectory is like this. When t goes to minus infinity, it goes here. But if you go approach to this boundary, this radius boundary, and again go back to the infrared region, maybe we can just cut negative t part, so that we can start from here and just talk about this falling particle. And there we can introduce parameter alpha, which is the separation between this real boundary and this minimum value of z of this particle. So this is some maximum excitation. So this is actually, because if we have put here particle here, it's this region where this roughly size alpha is excited. So that means this corresponds to exactly this alpha. So this is a simple excitation. That if we consider any excitation, it's very localized. It should go to have some description by some massive particles. That's a very simple mind idea. And there are some very nice methods which has worked out by Horowitz and Izaki to find the exact metric in this background. We just start from global radius with some black hole deformation, for example. And then we take this standard coordinate transformation from global radius to pure radius, but we slightly modify the metric by this m mass parameter. And then we get some slightly modified Poincare metric, which is exactly correspond to this metric. So we have particle is just here. It's localized at r equals 0 in global radius, but it's now moving along this previous trajectory. So we can construct exact metric. So we can compute energy density in any dimension. So we can do for any dimension. Basically, we can do the exact calculation, but it's somehow technically sometimes hard. So we mainly working on ADS3 case where we can get a nice exact result. But for other dimension, we can at least do some perturbative calculation in analytical way. So we explain the result for ADS3 here. So basic picture is like this. So previously I showed this energy density, and this is t equals 0. There are some very big peak here, and we have some peak, and they are separated some up at the speed of light. So we start with quench. So quench means we have some energy ramp, energy excitation, high energy region, and this peak is moves at the speed of light. It's really separated in left and right, so that this height becomes half. Go this way at later time t. So this is a basic structure, and so like this way. So this peak is going this speed of light going separate this way, and so I just write the picture, and we have some these two peak at later time t, and with width alpha, and as we will confirm by computing entanglement density, these two peaks are strongly entangled with each other. It's sort of entanglement pair. So first we can compute it.
Interpret this. Is this really like an excitation of the CFT, or is it more like
excitation
added real extra degrees of freedom?
No, we didn't add anything. Here it's everything normalizable, so just excitation in CFT. State. Yeah. And we can compute the entanglement density, so entanglement entropy. So we have particle here, and as you can easily imagine, we compute this subsystem A. We consider subsystem A and its minimal surface. And we have some particle going in and going out. So when this particle attached with this gamma A, this minimal surface, we have a large back reaction. We have this peak. So this is naturally easily understood from the viewpoint of this holographic or gravitational side. But it's not so. It's possible, but it's not so direct to interpret this result from CFT side. So that's the reason So the second one is we can choose this subsystem as its opposite side, and then we have some plateau appears because this region, this particular back reacts until they are sitting here. But so because of that, we can look at entanglement density. So this actually has a good description in CFT side, and indeed we can see some peak when L1 and L2 is the same. L1 actually negative and L1 is positive. So when L1 plus L2 is 0, that means we have 0 and it's separate this way. And this when these peaks coincide with this entangling points, then we have peak here. So this just says that if we talk about entanglement in this kind of setup, so we can measure this entanglement between this region and this region, but this is very small. But if we talk about the entanglement of this region and this region, it's very big because of this peak. That's what you can confirm in this calculation. But also, even if we look at the entanglement entropy, we get some interesting result. And we can take particularly limit L is much, subsystem size is much greater than the time. It's a really semi-infinite subsystem, and time is much larger than alpha. Then we get this analytical formula approximation in terms of this logarithmic function. This formula is very similar to the Cardian collaborative get in this local quantum range. Looks very similar. A is a real cutoff, UV cutoff, and alpha is the size of local excitation. But slightly they have a defined coefficient. But of course, their model is slightly different. This case, we have some really joined 2 points. But here we just start with connected line and we excite some points. So slightly we have some difference, but it looks very similar. And we can also compute some delta SA when we have this maximal value. So when this coincides this point. So this peak actually, roughly speaking, the case where we have some excitation, and this excitation, the range of excitation is coincide with subsystem A. Then in that case, we have this this peak maximal value, and we can compute this maximal value. This way, then we find that when this excitation is very small, it should be proportional to m, which is related to this first law, which I mentioned, and this is really some numerical number times mr. R is the alias radius, and m is the mass. And this is, if we interpret as some scalar field or field, it looks like delta. Delta is a conformal dimension, which is dual to some operator. So this means that for this excited state, we have some information, amount of information. It looks like this way. And if we exponentiate it, then we have some Hagedorn-like behavior. And this is not so strange. I mean, if we assume some deconfined states, this kind of behavior is not so strange. I mean, this is rather natural result if we have conformality with delta, which is very large, much larger than 1. And so, yeah, this is the exact result. And we can approximate by delta when delta is very small. And in the end, anyway, summary is this is actually another way to say this first law, but this amount of quantum information of some localized excitation is now up to some constant, but it looks like just energy. It's energy times its size. But this is, of course, very natural in conformal field. There are no other scale, but it's, we find this kind of very simple and basic behavior. So it looks very similar to Bekenstein, somehow seems to saturate or some related to some Bekenstein bound, which is quite interesting future problem. So which I have no idea.
How do you, I mean, this looks very classical, right? You have some classical energy lump, and it doesn't, a priori, it looks very odd to associate it with, you know, some quantum entanglement, because you haven't put in the information whether those things are genuinely, you know, quantum entangled or not. So how do you interpret?
I have no idea. This is rather quantum result because we use ADS-CFT, and just this is rather general result for an excitation of conformal field setting. If you have some energy excitation here, then that should have some amount of entropy. And this is just, measured this way. So I'm not sure how much it's classical. But calculation looks, of course, classical.
Right. I mean, it sounds like you have some lumps of energy that are sort of correlated because they have the same origin, but that's like saying, I don't know, tides of the Earth given by the moon would be sort of lumped up. If they're lumped up here, they're lumped up on the opposite side. And that's not, there's no, entanglement or anything between them. It's just the deformation has the same origin. That's why there's a correlation.
I'm not so sure. This anyway measures the entanglement between this excitation and the other part. Right? So this is one way to define this quantum information. But as you said, there are another definition of quantum information probably. So you can talk about maybe two lumps and how much they are entangled or something. Then we get of course differences.
Another way perhaps of putting the question is, in this setup, it really starts to look like bell pair entanglement, right? You make these two wave packets out of the component field theory, the excitations that are reasonably localized by the kinematics of the process.
Exactly,
and that's really like as if you do a literal PR type of experiment. And then I can ask the question, continuing on Veronica. So this kind of two-bit entanglement is at the heart of the working of the quantum computer. Can you use this stuff to compute?
Yeah, but of course this involves, that's quite interesting
very sharp.
point. But of course this involves quite a lot of degree of freedom.
Yeah.
So things are not so simple
It's
as
not
this
realized.
qubit one. Also this involves, I think, not the, we don't have spin, we can talk about just scalar.
It's not a called
So it's
mechanical
really-
degree of freedom, right? It's a lump of.
It's coherent somehow. And it's other, many different kinds of momentum modes which are entangled in this complicated way. So the structure looks very complicated, but maybe there are nice way to use this kind in the other setup. But sorry, I don't know what
Yeah,
but
it's clear.
it's
No,
interesting.
it's
Interesting.
I think it's a good question to ask always.
Okay. Yeah. So then I just quickly say something about the topic. It's this is quite basic question that to rewrite the Einstein equation in terms of some other formulation, especially here we call the quantum entanglement entropy. So basically, we know that the entanglement entropy is the area of the surface. So we should have some constraint on this area because we have constraint of metric by Einstein equation, and we can just rewrite in terms of this area, and we may get some constraint. But of course, this is naturally expected, but real calculation is very, very hard because this area and relation between area and metric is non-local, as is obvious way. So its translation is kind of not so simple. So but basically, what we'd like to do here is to analyze this kind of relation at the simplest case, which is a perturbative limit, perturbative Einstein equation. We just consider some small perturbation on the area space-time or some other space-time and just consider some perturbative Einstein equation, and we translate it in terms of some equation, constraint or equation for entanglement entropy. And so basically, we have a gravitational metric on the area space-time, which is Tx, z is the extra coordinate. So on CFT, of course, we don't have z, but instead of z, we have some L. L is the size of subsystem, and t is the time where we measure this entropy, and x is the center position of this. So we have some disentangling region, and we need to specify this center position. We can also do calculation here, but if we are in a translational non-invariant theory, so this entropy is different from this entropy, even though we have same error. So anyway, we have some same number of coordinates, which we have in area space-time. Also here, same number of coordinates we have in CFT side. So we want to roughly map these two guys. So, but this calculation of entanglement entropy is in general very hard if we have some very complicated geometry, because we have to look at we have to solve some minimal surface equation in complicated geometry. It's quite complicated numerical calculation. But in a perturbative order, it's very easy because And leading order, we can just use the same minimal surface before the metric perturbation. This kind of technique is often happens in probe approximation in ADS-CFT and many other things in theoretical physics. But anyway, so we have just gamma 0a, which is the minimal surface before the metric perturbation, and just integrate of this kind of function. Just integrate this kind of quantity. G0 is just the induced metric before metric perturbation. This is something just pure ADS, and we have induced metric on that. And in pure ADS, when this is a spherical round sphere, it's like really half sphere. Is a gamma 0a. This one is just half. We know this analytically. But G1 is a more non-trivial thing, which is a perturbative contribution, perturbative deformation of this induced metric on this surface. The surface is same as this gamma 0. Sorry, here I should put this gamma 0a. Gamma 0 should put 0 here. So this is something we can easily compute. So instead we integrate it out, we get. But still, of course, we have integral that means this non-local transformation. But somehow, in ADS case, we can solve this problem analytical way. So the result, it looks like this. Well, we can generalize this result for any dimension, but let's talk about ADS4 CFT3 so that this notational reason. So we take A to be a round ball so that we get an analytical minimal surface for pure ADS case. And its center is T and X. And this Einstein equation, we have of course Einstein equation. And this kinetic term, roughly speaking, is after some calculation. But this calculation can be easily done by using this kind of, formalism. And everything can be done analytically. So we have delta SA, and we want to find some equation which is satisfied by this delta SA. And this kinetic term is mapped to derivative L and X. X is a center position, and L is a size of subsystem. Right? This A is a round ball with this L. And we have some constant potential. This is actually related to this cosmological constant. And so it equals 0. If we are talking about a pure gravity theory, even that is dynamical in ADS4, and we can just set it equals 0. Very, very simple equation. We can even solve this in terms of Bessel function. But if we have matter field contribution like scalar field or fermion field or gauge field, then we have anyway field bilinear field, and that appears here as the expectation value in dual conformal field. So scalar field is dual to some operator, and its expectation value here. But this part is I just omit everything. It's a very complicated expression. There are quite non-local integral fields. But one thing I'm a bit surprised is that there are no time derivatives in this result. Somehow, of course, originally Einstein equation have a time derivative, but in the end, after some calculations, the very mathematical reason, in the end, time derivative disappears. Still, I'm not so sure about this interpretation. But this result is we can confirm directly this result from conformal field theory. There are several works in that direction already, and the result is correct, but somehow interpretation is very somehow mysterious. So anyway, this gives some constraint for holographic entanglement entropy at fixed time. And so we should because there are no time derivative, one may wonder that how we can determine this time evolution. But this actually comes from infrared boundary condition, which I didn't write it here. So we have Einstein equation, but at the same time we have to fix boundary condition. Otherwise, we cannot follow this time dependence. If you have a horizon, we need to impose the standard ingoing boundary condition, and so on. So that somehow we are missing here. So also this side it is missing. So that's the reason we don't have this time evolution in this formalism. So we can also do the black hole case, but its result is very complicated. But if the size of the subsystem is very, very large, actually it goes osmosis. Important part is only near the horizon limit, that is Lindlar space. And there the space is flat, almost flat space, Lindlar space, flat space. So the previous, this cosmological constant term disappears. And only the modification. And ADS3 case is very special because in ADS3 gravity, there are no, if we talk about pure gravity especially, there are no propagating gravitational waves. So we have two constraints rather than one. This is the same as the previous one, but essentially same as the previous one. But this first one is something new. And this dictates, this completely fixes the form of delta SA. This means left and right. Yeah?
Why is there a time derivative now when you said there was no time derivative?
Yeah. So this second one is very similar to this one. Yeah, so this is something we get here. Analog of this, we get here. But there are some new ones, which also, which involves this time derivative, especially only in this ADS3 case.
The second equation also has a time derivative, right? Or either
Okay. So sorry, we can just replace this x here. I mean, because we have this equation, so we can just write it x, and with some other. So sorry, this is not maybe not different. We can just replace this x here. Then the second one is.
I have another question. So suppose I just took a look at minimal surfaces. The problem is purely formulated in terms of some Riemannian problem, where I have minimal surface on a single spatial slice. So I should think roughly of this as the Einstein equation confined to that spatial slice. But why? I mean, so forget time dependence. Look at static states or timing states. So then we can work with minimal surfaces, and whatever constraint equation you derive from minimal surfaces should be telling you about the geometry of the surface of that slice. As you sort of vary your region size, you're sort of sampling sort of different aspects of that slice. So the constraint equation should be telling you about the geometry of just one slice.
Sorry.
Why is that constraint equation hyperbolic?
Yeah. Okay. So that's actually that's what I want to mention later. But anyway, so here we don't talk about deformation of minimal surface. This is the leading order. So we just keep the same minimal surface and compute the area. So this doesn't dictate the modified shape of minimal surface, I think, because this is a leading order calculation. This is a first thing. This only dictates the. This only shows this how this space-time is modified. Just how this metric is modified. That thing, and this hyperbolic, that is exactly important. I think it's quite important. But this is only we don't have a very intuitive understanding of that because of this hyperbolic. This is like a wave function, so we have something like that. This is not exactly right, but it's sort of, if we forget about other details, we get this wave function like behavior. And this tells us that if we, L minus radius is quite important quantity, and we should keep this finite. Should be constant, then we get the same result. So this is roughly says that if we locally excite some region, when this circle, this subsystem A, intersects with the local excitation, then we have non-trivial result. That means this becomes very, very big. But if we go slightly off from this, if the circle doesn't intersect with this local excitation, then this becomes trivial. So that is the only thing I can say, but this somehow roughly, suggests this kind of behavior. Because if we have a localization, if we have a local excitation, and if we subsystem A is, if they are separated from this excitation, there should be no interesting thing happens. Only if we have some subsystem A, which looks like this, and only if we excite this border region, there are some entanglement between them. If we excite this region, there are no interesting entanglement because this region doesn't change. Only this region changes. We have some entanglement pair in this region, and in this region it's non-trivial, but it's something like that. So if we have this kind of function which depends L minus x, then that means this part is fixed. Then we get same result. Same result means non-trivial. Right? So we have this, or we have excited region, and we take this one and this one. All this one has the same. This is L and this position x, and this L prime and x prime. This always have same value. So that should give some. But I don't have better. Maybe if you have any idea, please let me know. That would be really helpful. Yeah, I already done. So thank you very much.
Maybe one more just to wind up. There's none. So I have a question. So this, in classical physics, of course, you can have entropically favored phasors, and you've introduced us to this idea of a sort of quantum entropy and a temperature that we can associate with it. Instead of, we can decompose the energy into a combination of information temperature and information entropy. Can we think of the formation of, say, superconducting phasors in the ADS context as being driven entropically within your formalism?
Superconducting phase. Yes. There are several work. I also this Longen also working on this calculation of entanglement entropy in superconductor phase. So basically, it tells us there are some, basically it shows some presence of phase transition. But some cases, in my answer, some cases it's increased, some cases it's not increased. It's still, I think the interpretation is not completely understood, but it's interesting thing we should understand better about it. So I'm not the right person to give some comments on this.
Thank you very much. I think we should.